Hello everyone, and welcome to the video lecture for the heat transfer subject. Today we are going to continue our discussion about the radiation heat transfer. So today we will define the radiation functions, we will evaluate the emissive power for black bodies, and we will have see also the application of this concept or radiation heat transfer in a real life problems. So let me first introduce you the view factor. As you can see also in this figure, radiation between different surfaces depends on the radiation of surfaces and also it depends on the orientation of the surfaces, as you can see here, and also the radiation properties and temperatures of those surfaces. To find the effect of the orientation and the radiation heat transfer between different surfaces, we need to understand how much of the radiation which comes from one surface will strike to the other surfaces. We can define that by a parameter which is called view factor. View factor is defined to measure the effect of orientation and radiation heat transfer between two surfaces. And as you can see here, view factor is purely geometric quantity, and it is independent of the surface properties and temperature. It is only dependent on the geometry and actually orientation of each surface. So it is also called the shape factor, configuration factor, or even angle factor. By using this parameter, we can have the other definition, like diffusive view factor, which is when the surfaces are diffuse emitters and also diffuse reflector. If you remember from previous sessions, diffuse emitter or reflectors means the radiation from the surface or to the surface from the surface, which may be due to the temperature of the surface or due to the reflection of the another radiation from other surfaces. Is if it is uniformly it has a uniformly distribution, we call it diffuse reflection or emitters. And view factor which such a surfaces is called diffuse view factor. And we will have specular view factor when the surfaces are diffuse emitter but specular reflectors. In other words, we have a diffuse emitter but the surface is specular reflectors. Generally here in our calculation for our assumptions, we imagine that we just consider radiation exchange between diffuse surfaces only, and thus the term view factor simply means diffuse view factor. So from now on, in this slide or today's session, anytime I say view factor, I mean actually diffuse view factor. This view factor is usually shown by this symbol if as a view factor actually, and with two scripts, which those two scripts are related to those two surfaces which the radiation from one of them will strikes to the other one. So these if sub Ig is the fraction of the radiation leaving surface I that strikes surface J directly. As you can see here, this is surface I, inner surface, the surface of the inner sphere is surface I, the outer surface actually, and the inner surface of the uh, surface 2, here is the surface J. So the view factor from surface I to surface J is denoted usually by this form, but we can also write it like this. So the radiation from, and we call that, and we can read this like this, which it is view factor from surface I to surface J. The view factor F1, 2 means represent the fraction of radiation leaving surface 1 that strikes surface 2 directly. As you can see here, we have a radiation leaving this surface striking surface 2. So we call this fraction of the radiation as the view factor of surface 1 to surface 2, or simply F12. F sub 1 2. And one more thing is about its value. The view factor is the dimensionless value actually, and it is in the range of 0 to 1. It is 0 when none of the radiation ray actually strikes the surface 2, and it is 1 when whole or all of the radiation from the surface 2 is strikes to the surface 2. And we have a special case when the radiation from the surface will strikes to itself. As you can see here, for concave surface we have this case when the radiation from the surface will strikes to itself. So if from surface I to surface I actually, if the fraction of radiation leaving surface I that strikes itself directly, and as I told you, this F is between 0 to 1, and the view factor from surface I to J is 0 when no radiation from surface I strikes surface J, and it is 1 when all of the radiation leaving surface I strikes surface J. And as you can see here, this is a partial view factor, part of the radiated part of the radiation leaving surface I strikes itself. Here is 0 if 2 or view factor from surface 2 to itself is 0 because none of the radiation strikes itself, and also for the plane surface. So for plane surface and convex surface, the self view factor, actually you can call that like that, is 0, and for the concave surface it is not 0 actually, as you can see here as well. And when two surfaces with the surface area of A1 and A2 are radiating heat to each other, then we can write this equation, which surface area of surface 1 multiplied by or times by view factor from surface 1 to 2 is equal to surface area of surface 2 times view factor from surface 2 to surface 1. And we call this reciprocity, and it is a rule, and it will be used for our next calculation, and it will play a significant role to simplify our calculation actually. And we have some other assumptions when we are dealing with this view factor, which are the firstly, we think that the surface is isothermal. Isothermal means the surface of the temperature of the surface at each point of that is equal to the other point. So the temperature at the surface is uniform or isothermal, and also the surface is diffuse emitter. As I said before, here we imagine the surfaces which we are dealing with them, and we are going to calculate the radiation heat transfer are diffuse emitters. And as you can see here, it is a repetition of what I told you for different surfaces and the relationship between them. For plane and convex surface, the self view factor is actually 0. For the concave ones is not 0, and it is 0 when none of the radiation strikes the second surface, and it is equal to 1. The view factor is equal to 1 when from the surface I to J, when all of the radiation from surface I strikes the surface J. And why this is important? Why this view factor is important? Actually, we need to know how much of the radiation comes from the surface which strikes the second surface. And by knowing this this fraction, actually, we can understand how much heat transfer is happening due to this radiation. And as I told you, this fraction of the radiation can be defined by this view factor. So view factor is very useful because it shows the fraction of radiation leaving a surface and strikes another surface. In terms of orientation of the surfaces relative to each other, as I told you, radiation is dependent on the orientation of the surfaces. And the main assumption is that the radiation surface received from source is proportional to the angle the surface obtains when viewed from the source. In other words, from this, as you can see here, different surfaces, orientation, and this is the view factor for different surfaces. You can see it's different, and more of the radiation is absorbed actually or received by the surface 3 in this configuration compared to the other surfaces. The least one is for the surface 2, which is has least surface area toward the source of the radiation. So this is the case only when the radiation coming from the source is uniform. So we can use this fraction of this view factor actually when the radiation is uniform in all direction and medium between the surfaces does not absorb, emit, or scatter radiation. So this radiation from a surface to another one, it should be directly without any participating medium between them. Participating medium between them means something that can absorb or emit or scatter the radiation. So it is the case when the surfaces are isothermal and diffuse emitters and reflectors, and the surfaces are separated by a non-participating medium such as vacuum and air. This paragraph actually is important. In other words, we can use this view factor when the surfaces are isothermal, they are diffuse emitters and reflectors, and the surfaces are separated by a non-participating medium like vacuum or air, which are not effective on the radiation amount, or they cannot reflect it, absorb it, or emit it, or scatter it. Then how we can calculate this view factor? As I told you, view factor is a parameter which is only effective dependent on the orientation and geometry of the surfaces. So as you can see here, we have different geometries, and here are the equations to calculate the view factor for these different orientation and also different geometries. For two aligned parallel rectangles which they are located or placed in the distance of L to each other, and the size of, and also their size is equal actually, and the size of their side is x and y, then we can use this equation to calculate the view factor from surface I to j. So imagine surface I is the radiating surface, so this view factor from surface I to j, or the fraction of the radiation which strikes to surface j, can be calculated by this equation. As you can see here, it is only dependent on x, y, and as you can see here, L. For two coaxial parallel disks which their radius are rj and ra, this view factor can be calculated by this equation. So for this configuration, actually, when two disks are located from the distance of L to each other, and their radiuses are Ri and Rj, we can calculate the view factor by this equation actually, which is only dependent on their radius and their distance from each other. And for simplicity, we can define S as a parameter which is also dependent on the radius, as you can see here. And also for two perpendicular rectangles with a common edge, like this configuration, as you can see here, which their size is like this, x, y, z, then we can use this equation to find view factor from surface I to j, and so on. We have for this equation for 2D geometries. This one is 3D geometries actually. This table is for the view factor expression for some infinitely long 2D geometries. If you notice about the view factor, when we have some geometries like ducts or tubes or concentrical or coaxial tubes, like, let me find an example of that, like this one. Imagine this is a tube, then we can imagine that they are in 2D geometries. In other words, imagine this is the side of a duct. In this direction, this is x, y, for example. In z direction, it is infinitely long. So what we are interested about is only the view factor from this surface to this surface. So for different geometries like parallel plates with midlines connected by a perpendicular line like this, we can find the view factor from surface I, this one, to surface j by this equation, by knowing their width and their distance from each other. And for inclined plates of equal width and with a common edge, like this configuration, view factor from surface I to j can be calculated simply by this equation. And for perpendicular plates with a common edge, by this equation. So the view factor can be found by these different equation, and this is for this geometry as well, three-sided enclosure. We have this equation to find the view factor from this surface to the other surface. From I to j, for example, we can use this equation. From I to k, we can just rearrange this equation to find that as well. And for infinite plane and row of cylinders, imagine this is a plane, and this is row of cylinders then we can find the view factor from this surface to these cylinders by this equation, which is dependent on the diameter of the cylinders and also the distance between the center of those cylinders. So according to those equations, we can find view factor for different geometries by changing the size of those geometries. If you remember, this is two simple plates. The first one actually aligned parallel rectangles. You can see here they are located from this each other by a distance equal to d, and the dimension of them, the width and length of each one of these surface, as you can see, L1 and L2, and you can see here the relationship between the ratio of L2 divided by D and view factor from surface 1 to surface 2. As you can see here, by increasing in this direction, in other words, increasing the ratio of L2 to D, the view factor from surface 1 to 2 is increased. It can be simply understood also from the figure. As I told you, view factor means the fraction of the radiation which is strikes from surface 1, for example, here to surface 2. So as much as surface 2 is bigger, the size is bigger compared to the surface 1, or they are closer to each other, higher amount of the or higher fraction of radiation from surface 1 will strike surface 2. So L2 divided by D increased means L2 is increased, bigger surface, or D is decreased. In other words, they are closer to each other. So when the surface 2 is bigger or it is closer to surface 1, the view factor from surface 1 to 2 will be higher. And also you can see different curves for different ratio of L1 to D. As you can see also here with the same reasons, as much as this ratio is increased, the view factor is also increased. Ratio of L1 to D increase means this again this is bigger, the surface area of A2 is higher, or it is closer to surface number 1. Then it will receive higher fraction of the radiation, or the view factor from surface 1 to 2 will be higher until it reaches its maximum, which is 1. The maximum value of the view factor for two surfaces, as I told you before, is 1 when all of the radiation from surface 1 is strikes to surface 2. And also for the other configuration, we have similar graphs, which the view factor for this geometry is dependent on the size of W, which is the width of the surface number 2, and also its length, L2, as you can see here. As much as L2 is increased, this is, let me show. L2 divided by W is increased, F12 is increased, view factor from surface 1 to 2 is increased. L2 divided by W increase means this is bigger, okay, it will for sure receive more radiation from the surface, or W is smaller. In other words, if it's constant, if it is half of that, or can simply just work on the L2. L2 is increased, higher surface area for this one, and it will receive more radiation. And also for the L1, as much as this L1 is higher, this one higher radiation will probably strikes to surface 2. And also for this configuration, when we have 2 disks, all of these values is calculated by the equation which I showed you in the previous slides. But you can just see the variation of this view factor from surface 1 to surface 2 by these curves. How the radius, for example, in this equation, in this configuration, is effective on the view factor. As much as they are closer to each other, this view factor is higher. Closer means bigger L, or bigger this ratio bigger, or as much as R2 is increased or bigger, the view factor is increased. The bigger one for this, higher fraction of the radiation will strike to that from surface 1. And also this one, this is the for 2 concentric cylinders with finite length actually, as you can see here. The view factor from surface 2 to surface 1, this surface, the outer surface, this is the surface 2. From this surface to this one, actually from this surface to this one, the radiation can be is dependent on the view factor actually. That view factor from surface 2 to 1 is dependent on the their radius and also L. And as you can see here, as much as R1 compared to R2 is bigger, R1 compared to R2 is bigger, higher, it will have higher factor from surface 2 to 1. It is completely reasonable. As you can see, if this is a bigger surface, it will receive more radiation. And also this, if it is its length is higher, it will receive more energy or radiation actually, fraction of radiation, until it approaches to an infinite length. And in that case, the view factor will be when the radius of these two is equal, R1 is equal to R2, this ratio is 1, and when the L divided by R2 is infinitive, which means infinite length, the view factor will be the maximum, which is 1. All of the radiation from this surface will strike this surface. And so now you can understand and calculate actually how much of the radiation, or how much in terms of fraction, from surface 1 will strike surface 2. Okay, and that fraction is only responsible for heat transfer or radiation heat transfer. For two surface, we know that view factor. What about when we have more than 2 surface, like enclosure, which consists of n surfaces actually? Then for this case, we will have n2 view factors. In other words, from surface 1 to surface 2, 1 to surface 3, and 1 to surface 4, and so on, 1 to surface n. And we will have this for all of them. 2 to 3, 3 to 2. I mean, finally we will have n power 2 we will have n power 2 view factors. And we will use some fundamental relation or rules to find these view factor for such enclosures. We will use reciprocity relation. We have already seen that. We'll use the summation rule, how we can sum different view factors for different geometries. We will use superposition, and also we will use symmetry rule to find the view factor for different geometries and configuration. The first one, or the reciprocity relation, we have already seen that in the previous slides. It's AI times Fij equal to Aj Fji, which AI, this is, imagine this is two surfaces, surface I, surface J. So we have radiation from this surface to this surface. We are going to understand how much of the understand this, the fraction of radiation right from surface I to surface J. This is A1, this is A2. I have this relationship between them. AI Fij equal to AI Fji. When Fj when view factor from surface J to I is equal to view factor from surface I to J, we have this equality when AI is equal to Aj. Then simply we can cross out these two if the two surfaces is equal to each other. And when AI is not equal to Aj, also this the view factor from each surface to the other one will not be equal to each other. And for an enclosure that has n number of surfaces, the reciprocity rule can be used to obtain the relationship between these different view factors, and we will have this much number of the relationships for the view factor for that kind of the enclosures with the n surfaces. 1 divided by n times n multiplied by n minus 1 relationships we will find. Then by using the different methods we can find the view factor for all of the surfaces. What about the summation rules? Simply it means that when a surface, imagine this is an enclosure, is emitting radiation, it will strike all of the surfaces. As you can see here, this is an enclosure, but total fraction of the, all of these radiation actually is 100% of the radiation. Some percent of that or fraction of that will strike to each one of the surfaces. If we just add up all of the view factor, so this fraction of radiation from surface I to this surface, for example surface 1, is the view factor from surface I to surface 1. So, and for this one is for example surface 2, surface Fi2, view factor from surface I to surface 2. And the total view factor will be 1 because all of the radiation is striking to these surfaces. So the summation of the view factor from this surface to all of the surfaces will be equal to 1, which is the all radiation. So the sum of the view factor from surface I of an enclosure to all surfaces of that enclosure, including itself. That's the important some part of that. In this case, for example, if it is a flat surface, it will be 0 for itself, but here is a concave, so it has some kind of the self view factor. It will be equal to unity. So we can write this equation. If, for example, if we have 3 surfaces in an enclosure, we can write this one. From surface 1 to surface 2, surface 1 to surface 2, surface 1 to surface 3. Actually, this is surface 1 to surface 1 itself. view factor, and it should be equal to 1. This is another equation which we have to find this view factor for different surfaces. The other rule which we can use to find the view factor for enclosures or different configurations is the superposition rule. Simply, it says when we have one surface 1 like this and its radiation strikes two different surfaces, the whole those two surfaces actually are in the arrangement that can receive the radiation from surface 1. Then the view factor from surface 1 to one of those surfaces plus the view factor from that surface to the other surface will be equal to the view factor from that surface 1, for example, to both of those two surfaces. Simply, we can write like this: F1 to surface 2 and 3, both of them is equal to view factor from surface 1 to surface 2 plus view factor from surface 1 to surface 3, as you can see in this figure. So the view factor from surface I to surface J is equal to the sum of the view factor from surface I to the parts of the surface J, like this configuration. And this is helpful when we cannot find the view factor for part of the surface. For example, if we know the total and if we know the part of that, then we can find the other part as well. And if we multiply this relationship, we can find this for each surface. So we can use these superposition rules when we have a configuration which we cannot find a view factor for some part of that, but we can find for some the other part of that surface. Simply we can go to that table or figure that I show you, then find for that part which we have equation for that. Then simply if we have, for example, this configuration and this one, then from the table, then we can find this one by knowing this equation. So by multiplying two sides of that superposition rule to A1, which is surface area of the surface 1, and applying the reciprocity relation, we can find this equation, as you can see here. And by rearranging of that, we can find this, as I told you before. This is the view factor from surface 2 and 3 to surface 1. From this surface to surface 1. Simply, we can find that by this equation, for example. This is an example how we can find view factor from a complicated surface that we don't have a equation or a relationship to find the view factor for that. Simply we can use this relationship because we know the view factor from surface 2 to surface 1, from surface 3 to surface 1, and we know their surface area. Then we can simply find the view factor from surface 2 and 3, which is a combination of these two, to surface 1. And the fourth and last rule we can use to find the view factor for different geometries is the symmetry rule. Simply, you can see here, when we have a symmetrical arrangement between two different surfaces against another surface, we can use this equation, which means the view factor from surface I to surface J, for example, is equal to view factor from surface I to surface K. So view factor from the surface to each one of them is equal. And by using this reciprocity rule, in other words, by multiplying the values to their surface areas, we can simply rewrite it like this. If J to I, view factor from surface J to I, is equal to view factor from surface K to I. So for two or more surfaces that possess symmetry about the third surface, like what we have here, we'll have identical view factors from that surface equal to this one. Sometimes we are interested to find view factor for darts, which in one dimension or direction, actually we can imagine it is infinity, the size of that. So we can use the cross string method, actually we call that cross string method, to find the view factor for them. So view factors between infinitely long surfaces, surface 1 and 2. Imagine this is a dart. We are interested to find a view factor between surface 1 and 2. We can use these cross string methods. Simply, it is we can use this equation. Imagine this is surface I, this is surface J. So view factor from surface I to J is equal to summation of cross strings minus summation of uncrossed strings divided by 2 times strings on surface I. What is the strings? The strings mean you should draw something like this. You should connect all of the point on that at the end of each surface to each other by these strings. Then find the crossed strings. For example, if we are interested to find view factor from this surface 1 to surface 2, we can use this equation. Summation of cross strings. Cross strings mean L5 and L6. So L5 plus L6 minus uncrossed, summation of uncrossed strings. Uncrossed strings are L4 and L3, as you can see here, divided by a string on surface 2 times a string on surface I. This is surface I, and L1 is the strings on that surface. So we can use this equation to find the view factor from surface 1 to surface 2 when we have this condition. Infinitely long surfaces like channel and ducts, which have very long in one direction and relative to the other direction, actually, and we can imagine they are two-dimensional configuration or geometries. Okay, up to now we have learned how to calculate view factor for the surfaces with those assumptions I told you, with isothermal temperature at the on the surface, the diffuse surface. But sometimes we have surfaces which are corrugated, like what you can see here, and we have too many reflections on those surfaces, and it is really complicated to find the radiation transfer between, and it is hard actually to find the radiation from those surfaces. So we can simply approximate these surfaces as black bodies, and we can imagine these surfaces as not any reflection. There isn't any reflection for such surfaces. Surfaces which are corrugated, and reflection in each point of that is different from the other points, so it is hard to find the reflection radiated which is reflected from the surfaces. So we can imagine it is black body's surface and does not have any reflection. So in this case, if you remember, we had radiation which leaves the surface at rate of EB, which is for black bodies, equal to sigma T power 4, which T is the temperature of that surface. And we call this emissive power, if you remember from previous slides. The radiation which leaves the surface has this amount of the power, which is dependent on the temperature of the surface. And for black bodies, as I told you, we don't have any reflection, so all of the radiation power actually, or emissive power, is equal to sigma T power 4, which is only due to the emission from the surface. And if you remember also, the view factor F1 to 2 means the fraction of the radiation which from surface 1 strikes to surface 2. By knowing this information, we can find the net rate of radiation heat transfer from surface 1 to surface 2 by this equation. Q dot 1 to 2 means the net rate of radiation transfer from surface 1 to surface 2 is equal to radiation which leaves the entire surface 1 and which it strikes surface 2 minus radiation leaving the entire surface 2 and strikes surface 1. Simply by substitution their values, radiation leaving the entire surface 1 means EB1, or emissive power of the surface 1, and the fraction of that which strikes surface 2 can be found by this view factor. Now you can understand why this view factor is important, because only that part of the radiation which strikes to another surface, from one surface to another surface, is responsible for the heat transfer or radiation heat transfer. So this is the amount of the radiation heat transfer from surface 1 to 2. This is amount of the radiation heat transfer from surface 2 to 1. And if we are interested to know the net rate of radiation heat transfer from surface 1 to 2, we should use this equation. This amount minus this amount. And by knowing this reciprocity relationship and by substitution EB, or emissive power, by sigma T power 4, we can rewrite this equation like this, which the net rate of radiation transfer from surface 1 to surface 2 is equal to A1, or surface area of surface 1, view factor from surface 1 to surface 2 times sigma T1 power 4 minus T2 power 4. T1 and T2 are the temperature for the surface 1 and surface 2, and sigma is Boltzmann constant. And as you can see here, if F1 2 is 1, it means all of the radiation from surface 1 strikes surface 2. This will become A1 sigma T1 power 4 minus T2 power 4, which is a simple equation we had in previous session. And when this is 0, it means no radiation strikes to surface 2 which comes from surface 1. So the rate of heat transfer between two surfaces, which view factor for them is 0, will be 0. heat transfer only happens when the radiation from a surface strikes to another surface. It will be positive. When it is positive, this Q dot from surface 1 to 2 is positive when we have heat transfer from surface 1 to 2, and when it is the result will be negative when the direction of the heat transfer is in opposite direction from surface 2 to surface 1. This will be negative. So the sign of this calculation, the result of that will show the direction of the heat transfer. And this equation for an enclosure which has in black surfaces actually, or simply in surfaces, which we can imagine that are black surfaces without any reflection, only emissive, they have emissive power, this equation will change to this one. So Q dot I, in other words, net rate of radiation transfer from surface I to all of those surfaces, is equal to, if you remember, this is a summation relationship actually. So the rate of heat transfer from surface I to all of the surfaces is equal to rate of net rate of radiation heat transfer from surface I to each one of them plus each other. Simply we should add up all of the heat transfer from that surface to the other surface.